Welcome back, everyone. In this video, I will be continuing the section on optimization. So number 2 here, it says find the point on the line y equals 2x plus 4 that is closest to the origin. So whenever you find something closest to something else, you're gonna think of the distance formula. So let me make that a little bit smaller, but I want to go ahead and just draw the picture a little bit to be able to explain the problem. So let's put the origin here. This is our origin. 0, 0, and then we have the line y equals 2x plus 4. Now that's the line with y-intercept of 4 with slope of 2, so it's positive. I'm not really going to specify the other points. You can figure out the x-intercept if you want to, but it's not going to be important to finding the answer to the problem. But what you're really doing here is basically calculus is going to really let us run through every possible coordinate pair, every x comma y here, and it's going to tell us which one is closest to this point. So it seems unreasonable that the point down here would be closest because something right here would be a lot closer, but we don't really have to specify and check anything. So pretty much anything sort of around this piece we would expect to be the closest. After we get past here, it's getting further away, and down here it's also getting further away, but it's just going to take care of the whole thing for us. Now, once again, when we're finding something that's closest to something else, we want the distance formula. And the distance formula I'm going to label with the letter D. That equals the square root of x2 minus x1 squared plus y2 minus y1 squared. And you have everything you need to actually know how to plug in x1, x2, y1, and y2. You just have to realize how to do that. So one of our points is the origin because it's going to be what we're finding the distance between this and something on here. So this is going to be my x1 and y1. x1 is 0 and y1 is also 0. Well, what is my x2 and y2? Well, it's going to be any point on this line. So any point on this line at all. The problem is we don't really have a possible way to just plug in numbers for this. So the easiest thing to do, a point on this line could be represented by x comma y. This would be our x2 and y2. We have x and we have y. Now let's go ahead and plug it in. So when I do that, we have x minus 0, which is just x. So this becomes x squared plus y minus 0, which is just y. So we get y squared. But we want to minimize this because we want the closest. And obviously a good hint that we want to do the minimum or maximum is because we are in this section. But closest means do the minimum. We want to minimize it. And in order to minimize it, we need the derivative. So we need just one letter here. Well, luckily, you know how to plug in for one letter because of the formula. X comma y is a point on this line, but we know how to figure out y if we have x because we have a formula. Y equals 2x plus 4. So what we're going to go ahead and do is plug that in. And when we do that, we've got d equals the square root, x squared is fine because x is going to be the letter that remains. Now, if this was x equals something with y, then we would plug it in and have just y remain, and that would be fine. And then we have plus 2x plus 4 squared. So that is for the y squared. And now we want to go ahead and just simplify this because we're going to do the derivative of this. And in general, yes, factored is nice. But when it's factored, when you have a plus in between, it's not actually that nice. So we're going to go ahead and just make it easier on ourselves and multiply this out. So 2x plus 4 times 2x plus 4. And then go ahead and FOIL this. We got x squared, and 2x times 2x is 4x squared, plus 2x times 4 is 8x, plus 4 times 2x is 8x. Plus 4 times 4, which is 16. All right, and go ahead and simplify. One more step is just to combine like terms. And we have x squared plus 4x squared is 5x squared plus 8x and plus 8x is 16x, and then plus 16 at the end. All right, so we have our actual distance formula for this situation, meaning if we plug in an x value, let's say -1, somewhere around here, just on the negative side, then it'll tell us the distance. If we want to plug in +1, maybe over here, it'll tell us the distance. but we want this minimized. So we need to do the derivative. And we want to find the critical values. All right, so let's go ahead and do that. Now, when we know when we do the derivative, we never like to use a radical. So let's go ahead and just realize that this is a regular square root, which means it to the 1/2 power. Now we do the derivative using the 1/2 power. And I'm going to go ahead and write d prime, because it's kind of weird if you write d over dx to represent the derivative, because there's already a d. So I'm going to use d prime. And to do the derivative here, we bring the 1/2 down, rewrite the inside, 5x squared plus 16x plus 16. Subtract 1 from the power becomes negative 1/2. And then you multiply by the derivative of the inside, which is 10x plus 16. Right. And we want to find the critical numbers, which means we want to set this equal to 0. But we do have a fraction in here because this is a negative exponent. If we go ahead and make it positive, then what's on the top is you have a 1 and you have the 10x plus 16. So just 10x plus 16 on the top. It's all multiplication. And on the bottom, you have a 2. And this is going to multiply the 5x squared plus 16x plus 16 to the 1/2 power. It becomes positive. Well, our knowledge of finding critical numbers would tell us we need to set both the numerator and denominator equal to 0. But what I want to point out, and this always happens with these distance problems, is that this right here, this is the formula for the distance. And now if you trust yourself in that you set up your equation correctly, the distance is never 0. It's always positive, because the distance between this point and a point on this line is never 0. And distance can't be negative. So that means this is always positive. Specifically, it cannot be 0. So we don't even have to set the denominator equal to 0. What would happen if you set this equal to 0 and solve it is you would get some imaginary numbers. So we don't have to worry about that. And of course, multiplying by 2 wouldn't change it because it's just going to keep it positive. So all we have to do is to find the critical numbers is set the numerator equal to 0. We have 10x plus 16 equals 0. And you solve this, you can subtract 16 from each side. You get 10x equals negative 16. And then you can divide each side by the 10, and you get x equals negative 16 over 10. Simplified as a fraction is negative 8 over 5. And this is kind of a nice decimal, so I'm going to actually use negative 1.6. But you can also use negative 8 over 5, whichever one you want. All right. Now, as far as the distance problems go, we have to be careful how we proceed. So two things you're typically asked. You'll either be asked to find the point, which we are here. We want to find the point. That means we want the x comma y pair, and we have the x. Now I'll explain why this actually minimizes it in just a second. The other type of problem you might be asked to do is find the actual distance, a minimum distance, which this one isn't. But to do the other one, all you would do is take this negative 1.6, what we got for x. You would plug it in your distance formula, which I would do here. The one where you already simplified, you would plug in negative 1.6 for x here, and that would be your minimum distance. Now for us, we want to find the point. So instead of plugging it in to get the distance, we want to just plug it in here to get the y value. Right, that's our y formula. It's the only way we know how to get y from x. So when we plug y equals 2x plus 4, and we plug in our negative 1.6 for x, we have 2 times negative 1.6 plus 4. Negative 1.6 times 2 is negative 3.2, plus 4 is 0.8. So the closest point, the x value we got was negative 1.6, and the y value was 0.8. Right, now technically we haven't super checked that this is the minimum. We just found a point that is a critical number. We plugged in to get the y value. Why is this good enough? Well, I can sort of explain it from the picture on why this is going to work, and it will always work if you have just one number. for the critical number. So this is in quadrant 2. Now I'm not saying it's exactly right here. It could be farther up here. It could be lower, closer to the x-axis, but x is negative and y is positive, so it's in quadrant 2. But the idea is, you know, as you move farther away, as long as you have just one critical value, as you move farther away, the distance has to get farther away. If it was going to get closer, then you're going to have a point where it gets the closest again, and then it's going to start increasing. So that would be another critical value. So when there's just one, it has to get farther away both ways. Now, the way you can check this, if you have more than one, and I'll go ahead and write this on the side because we don't hear, but if you have there's kind of two ways to do it. One is to make a sign chart, which is always nice to do, but the sign chart might give you that you have multiple minimums, and then you still have to choose which one's smaller. So it's going to boil down to this. If you have more than one critical number for this type of problem, what you want to do is plug in all critical numbers to distance formula. So right here, we would want to plug it in right here, the simplified distance formula we have, and keep the smallest. So the x value that makes the smallest number for the distance. So if you have 2, then you just plug in both. One of them is going to be smaller than the other. If you have 100, which of course that won't happen, but if you had an insane amount, you would still do this. But the fact is, when we only have one, we don't have to do anything extra, and we can stop there. Right? And that is really an ideal, but also pretty normal kind of question as far as finding the minimum distance. We usually use a curve, y equals something, or it could be x equals something, and it's closest to another point. The origin is always a nice point to be closest to, but it doesn't really make it that much easier, because if we had, let's say x was 1, then you'd have x minus 1 here. Well, you would just FOIL it out and then go through the same exact process. It's just slightly more work. It's not really much of a difference. Right, now for number 3, this is like really the last kind of problem that you can deal with optimization as far as the way it's set up. The first one, we had a shape. It was a weird shape, but we had a shape. We made an equation from that. Another normal example was the previous one, where we had to figure out something using the distance formula, figure out the closest point. This is just an application from, let's say, a biology type of thing, or chemistry based on the problem, whatever you're reading, but it's already given us the formula. So we just have to focus on the math. We don't have to come up with this formula. And I have no idea how to do it anyway, because I don't know anything about agricultural crops. Well, let's go ahead and read the problem. It says a model used for the yield capital Y of an agricultural crop as a function of the nitrogen level in. I do want to point out what that means. This means like n is the variable. Any other letter in our equation, which you can see there's a k here, is not going to be a variable. It's just capital N. And it's given by y equals this k times capital N divided by 1 plus n squared. Actually, I can go ahead and write in parentheses like x. So some people when I've dealt with teaching this in the past, they don't like using anything besides y and x, which you just want to get comfortable using different letters. That's why we use them a lot in this class, but it's kind of like our x. Our capital N is going to be like our x when we do the derivative. Right, now k is a positive constant. Whether it's important that it's positive or not remains to be seen. It might be important that it's positive, but the main thing is that it is just a number. So all a constant means is it's just a number. And it must be the fact that it's not important to know what k actually is to do this problem. So the question is, what nitrogen level gives the best yield? So what this is asking us to do, think about what best yield means. Well, the yield Y of an agricultural crop is just the amount you get. So the more the better. But we want to maximize y, which means we find the critical numbers of it, figure out which one's the biggest when we plug it in, and that would be our maximum. So we want to make sure we do that. And all we want to do when we're solving this is we want to figure out the nitrogen level. So we want to maximize y by finding n that does that. All right, well, if we want to maximize this formula, we want to do the derivative. Pretty much what we are capable of doing in this problem is we're really just skipping to the part where we already have the function. Like here we are when we established the distance formula, and we're just going to do the rest. We're going to find the critical numbers, and if there is more than one, then we'll have to worry about it. If there's only one, then we don't have to worry too much. We could just check or understand that it makes sense that it is the best. All right, so let's go ahead and take care of this problem. We want to maximize, which means we want to do the derivative. Now I'm going to write this as dy over dn because it's not a d, but you could also write it as y prime. Funny looking y. But the reason why it's dy over dn is n is our variable. Now when we do the derivative of this is a division, so we're going to use the quotient rule. Now the derivative of k times n, that is just k, because n is like x and k is a number. So pretend if this was 2x, the derivative of 2x would just be the 2. But instead of 2, we have k. So it's just k, and it's multiplied by 1 plus n squared. Then we have minus the top, which is k times n, and then multiplied by the derivative of the bottom. The derivative of 1 plus n squared is 2n. And remember that the derivative was with respect to n. So there's no chain rule here. Every time we see an n, we just do the derivatives just like when we have x. So that's 2n, and it's over 1 plus n squared squared. All right, so let's go ahead and simplify this because we know we want to set it equal to 0, but we need to simplify it first. I'm going to go ahead and distribute the k through. You get k times 1 is k plus k times n squared minus, and then we have k times n times 2 times n would be 2k n squared. And you can continue simplifying because we have a k n squared minus 2k n squared would be negative 1, or just negative k n squared. Okay, so just we have one of them, we have 1k n squared, and then we take off 2k of them, so we are left with negative 1k of them over the 1 plus n squared on the bottom, and that's squared. And you can actually go one more step if you want and factor the k out. So we have k times 1 minus n squared over 1 plus n squared squared. Now that is the fully simplified derivative. So if we want to make super sure that we are going to make the rest of the problem easy as possible, we have done it. Now, you can factor 1 minus n squared, but when we set it equal to 0 and solve it, it's not going to change anything, so I'm not going to do that. All right, now we want to find the critical numbers. We want to set the top and bottom equal to 0. So the first thing I'm going to do is do the top. K times 1 minus n squared equals 0. Label this as finding the critical numbers. Now k is just a positive number, so this actually is important that k is at least not 0, because if k was 0, well, this equation would be irrelevant because the top would be just 0, but also you couldn't divide by 0. So it's kind of important that it's at least not 0. It could have been negative and this would still work. All right, and we have 1 minus n squared equals 0. Now solve this for n. You can factor it, or you can just add the n squared to each side. So you get 1 equals n squared, and then do the square root. Now when you do the square root, we know because it's not a 0 here, we do need the plus or minus, and we get n equals plus or minus the square root of 1, which is 1. Now if you're like me, you don't know a lot about nitrogen, but what you could reasonably understand is that the level of nitrogen, or the way I think about it in my head, is the amount of nitrogen cannot be negative. right? You can't have negative nitrogen in soil, so negative n does not make sense. It must be at least positive. We cannot have negative nitrogen. All right, just pretty much like any physical quantity. You can't hold negative anything. You can pretty much just see negative things, like unfortunately negative numbers in your bank account or something. But you can't hold negative numbers. So we do get n equals 1. And that seems like a reasonable answer because at least it's positive and it makes sense. And it's not a really weird number. Now, the question is, what happens when the denominator equals 0? Well, there's kind of two ways you can do it. You can solve this, or you can actually realize that this is never actually 0. So I encourage you, if you're not comfortable with what I'm about to show you, to solve it, but I'm going to show you real quickly why it's not ever 0. And the way I'm going to do it is I'm going to pretend this is x instead of n. I'm going to graph y equals 1 plus x squared. Oops. And then I'm going to square that. Well, what does the 1 plus x squared? That's like our parabola, and it shifts it up 1. So if I get rid of the squared for a second, oops, and get rid of that, it's like our parabola shifted up 1. Well, the lowest it goes is positive 1. That's the vertex. Well, what happens if you square something? It doesn't do anything but make it positive. It kind of makes it more positive in a way, because if you square 2, it becomes 4. If you square 4, it becomes 16. But the point here is that if we want to set this equal to 0 and solve it, we would be finding the x-intercepts. And this can never be 0. It can never be 0 because this is at least 1. And if you square something that's at least 1, it's never going to be 0. Now, if you're not comfortable with that logic, there's nothing wrong with just solving this. You can solve this. You just start by doing the square root, subtract the 1, and then do another square root, and you'll get a negative square root. But one of the things I think that's important about calculus is realizing, over time, by being exposed to it, when things don't have answers and not having to go through and solving them. So this has no solutions, and it's because 1 plus n squared is at least 1. It's never equal to 0. No matter what you plug in for n, it's always at least 1. All right, so we got one critical number, and based on really the first two problems, we hope that, it's our right answer, but this one's not a distance. So it doesn't make nearly as much sense to logically say, well, this has to be the biggest, because as we go further away, it's going to get smaller and smaller because we are trying to maximize. So how do we go through and check that something is maximized? Well, we can do a couple things. Probably the best thing in this one is not to do the second derivative test, and otherwise it is to make the sign chart. Just to verify. Now, if you just went ahead and looked it up or figured out, you would actually see that n equals 1 is the correct answer. But what I want to go ahead and do is just do the sign chart just to reinforce that, in the first problem, we did the second derivative test. The second problem, we just used logic. And then the third problem, this one, we're doing the last real option, which is the sign chart. So we have our 1 value, n equals 1. And then we want to do what? We want to go ahead and plug in numbers on either side to see what it's doing for the derivative. So I'll plug in 0 and 2, and we know we plug into the derivative. All right, so let's go ahead and do that. We call this y prime, so I'm going to call y prime of 0 and y prime of 2. I apologize, I don't know why I can't draw capital Y's very well. But go ahead and plug in these values for n. Remember, k is positive, so we're plugging in for n. We have k times 1 minus 0 squared over 1 plus 0 squared squared. Right, and the top here is k times 1 minus 0, which is just k, and the bottom is 1 plus 0 squared, that's just 1 squared is 1. So that's k, which is greater than 0. Now that's another point where k being positive is important. So this is increasing. It's looking pretty good because we want a maximum here. We want to see that it's a maximum, and then this graph sort of looks something like this. It's going to go up and hopefully it's going to go back down. All right, so as long as y prime of 2 is negative, we're good. Go ahead and plug in n equals 2. We've got, let me actually draw an arrow down here like this. We've got k times 1 minus 2 squared over 1 plus 2 squared squared. And now the top here, we have k times 1 minus 4, which is negative 3, over 1 plus 2 squared, that's 4. So this is 5 squared, which is 25. Now, based on what we said above, you should not be surprised that the denominator is positive because it's always positive. But the numerator this time is negative because we have negative 3k over 25. Since k is positive, this is less than 0. But this is negative, which means we do actually have a maximum here. And because it's the only critical number, what that's telling us is that it can't come back up and start increasing again. It's the absolute max. It's also a local max, just based on our terminology from prior sections, but because it's the only one, it's the only critical value, that means that it cannot possibly come back up. It's going to go up, hit our absolute maximum, and then come back down. You can even go farther and graph this thing. So y equals, you don't know what k is, it's just a positive number. So I'm going to pretend it's 1 and graph y equals n divided by 1 plus n raised to the 2. And Desmos can graph with any letter you want, but if you throw a k in here, it's probably going to mess up because it doesn't know what k is supposed to mean. So that's why I plugged in k equals 1. But the point here is that if you look at where n is 1, which is the x-axis, so right here, that's actually our maximum. And it makes sense. So you could do this with any function, is just go ahead and check it. But the idea, of course, with optimization is we don't want to just graph it. We want to go through and do the steps. Right? And I guess another thing I should have mentioned was, keep in mind that technically we had 2 critical numbers. One was -1, but the nitrogen levels aren't negative. So this is kind of our starting point. That's at n equals 0. Everything to the left of this is not really a part of our graph that we care about. All right, but that is optimization in a nutshell, and I will see you in the next section.